Right. In this video, we're going to be looking at kind of the visual definition of completing the square. When we talk about completing the square, typically we're talking about something that looks like this, a quadratic, because it's a square. And what could we put in the blank here to complete the square? But this actually comes from a geometric understanding of how we can multiply polynomials or simple binomials together in order to get an expression that normally looks like this. So here notice that we have x squared. Well, x squared literally means a square that is made up of sides x and x. We're adding that to bx. Well, because this isn't a square, that's actually a rectangle, where one side is b and the other side is x. When we look at that, if I were to put these two things together, I would just have a larger rectangle. But because they share this side x, we can actually do something pretty cool, and we can split this box in half. When we split this box in half, we can move this bit, so notice here, down to the bottom, and we get something that looks like this. So we still have our x squared here. This is now our b, but it's been split in two. This length all along we knew was x. And we have this bit here. Notice it's just missing a piece. And this piece is b over 2 squared. We're going to look at why it's that. But I want you to get this idea of when we're talking about completing the square, yes, it's an algebraic expression, but actually we're looking at visually, how can we complete a square? How can we figure out the area of this missing piece? So the first example we're going to look at here has to do with, well, instead of x, what if it was 6? So in all those places that I had an x of before, I'm now going to have a 6. So this large square is going to be 6 by 6. And because notice it was x squared. And then the other one was b by x. It was b by x. So this length here also is going to be 6 in this case. That represents all of these kind of lines here. And I'm trying to draw them on the lines so we know they're not the areas. Our b value then is going to be 2. So once again, the first thing we did after we kind of get that on here is we actually split this in half and brought half of it down here. So 2 divided by 2 is actually a 1. This becomes a 1 here and a 1 here. A 1 here and a 1 here. This pink piece is what we're going to try and figure out what should that area be in order for this to actually be a square. Because right now we only have the yellow and orange pieces. So if I'm looking at this larger square and I'm trying to figure out, well, how would I find the area of this? Well, I know that to find the area of a square, it's the length times the width, or the side squared. So I see that my side is made up of 6 plus 1 times the other side, which is also 6 plus 1. So I'm not 7 times 7, which is 49, and it is geometry, so this would be unit squared. So this is 7 and this is 7, so this entire square should be 7 squared, which is 49 units. But if I add up what I currently have, and change colors here, the area of this large box, well, was 6 times 6, so that's 36. These small rectangles were 6 times 1, 6 times 1. So I currently have 36 plus 6 plus 6. If I add all of those together, I get 48 units. So the question is, how much needs to go into my pink square? Well, I need 49 for it to be a square. I have 48, so the area of this square needs to be 1 unit squared. I have now completed the square. I figured out what is the area needed in order to complete it. If we kind of think about this also, we know that because these are rectangles, if this side is 1, this side is also 1. If this is 1, this is also 1. We can do 1 times 1 equals 1, and we can see that we have the same answer. So this was looking at it very much just using numbers and really trying to think about what did this area need to be in order to make this a full square. We can go back and add some more variables to this. So now I am back at x squared. That represents my big yellow square. So x times x. And this is x squared. My rectangle is going to be 6x, so 6 and x. When I split this 6, this becomes a 3. That means this also becomes a 3, because remember these are just halves. Which means the area of both of these orange ones is 3x. I can do that same idea of, well, what would be the area of the entire square? I can see that now my side lengths of my entire square are x plus 3 and x plus 3. So if I have an entire square, it's actually going to be x plus 3 squared. But I want to multiply this out to kind of get it into this format above because I'm trying to figure out what needs to go in this blank. So if I multiply this out, I get x squared plus 3x plus 3x plus 9. So it should be x squared plus, sorry, that should be a 6. 6x plus 9 is what my whole expression should be. Currently, in what I have x squared plus 6x. So what do I need? I need to plus 9. So that means this right here should be 9 units. Once again, we can double check that. This should be 3. This should be 3. 3 squared gives me 9. So that is what we should have here. If I was to actually complete the square, I need to add 9 units. That's what I need in order to make this a full square. So the last little bit, this is kind of how we do it, but it's to talk about, can we go between the two forms? So I now know in order for this to be a square, it needs to be x squared plus 6x plus 9. But often when we're solving, we're going to want this in our factored form, which is really what was squared is what we're asking here. Well, that just represents your side length. It was x plus 3 times x plus 3, which we can rewrite as x plus 3 squared. And this is how we see that square algebraically, is to show that what we really did by adding this area here, we created a square where each side length is x plus 3. So now that we've seen this purely in numbers, and we've seen it with some numbers and some variables, let's use the same idea to create what we kind of consider the rule, which is what we saw on this very first slide, this idea of why is this here b over 2 squared. So we're going to do the same idea. We like our x squared to be our large square that we have here. This is our b. And when we get to this point, we know that to exploit it, we have to take this number and we have to divide it by 2. So this becomes b over 2, b over 2. We have to figure out what's going to go here. So there's kind of two ways we could do it. We could do this the long way out again and say, oh, this should be x plus b over 2 times x plus b over 2. We can multiply this out. Here, if I look at this, b over 2 times b over 2, well, it's a fraction, so b times b is b squared over 2 times 2, which is 4. Or we can think about what we actually did there was b over 2 squared. We took the b over 2 and the b over 2 and we multiplied it by itself. So this is going to be x squared plus bx plus b over 2 squared. That's really just showing you that we found our side lengths and we know that this last bit is what we're completing. That's what this area has to be. This is the very algebraic way of kind of seeing that. We can also come over here and say, well, hold on. If this is b over 2, this is also b over 2. If this is b over 2, this is also b over 2. I have a perfect square where each side length is b over 2, so the area of the square is b over 2 squared. So once again, it's that same idea. So we can take this. This is the standard form version of our rule. If you have x squared plus bx plus b over 2 squared. We rewrite this in its standard form as, notice that it would be our side lengths of what we have here, x plus b over 2 squared. This is quote unquote the rule of how we complete the square. So now that we've seen it visually, let's see if we can actually put this into action. Can we figure out, without having to draw this whole diagram, what should go in the blank? So we're going to start with this one. I know that it's all about my b over 2. So the first thing I'm going to do is I'm going to take my b value, and I'm going to divide it by 2. And then we know that it's b over 2 squared, because we're doing that, we're trying to find that area of that small square. So we're actually going to square whatever we get here, which is 5. It's going to be squared. Bam, that's what goes here, which is 25. So notice once again, all I did is I took my b term, I divided it by 2. Whatever I get here, we square. That's actually what we need in order to complete that square. So in the earlier example, it was 6. We took 6, we divided it by 2, we got 3. And 3 squared is what gave us the 9. That's what we needed to add into our blank. The rule said take your b, split it by 2, and that's what you square to figure out what goes in your blank. The other thing is putting in factored form. We said our factored form is always going to be x plus b over 2, everything squared. So in this case, my b over 2 was 5. Whatever you get here, this is what goes in here. So I end up with x plus 5 squared. This is equivalent to this. So this one was a little bit simple because this divided by 2 really easily. Let's do one more, slightly harder. So same idea. For this blank, the first thing I need to do is I need to take my b term, which is -7, divide it by 2, and square it. I'm going to ask myself, does this simplify? And it doesn't really. So when I'm squaring a fraction, you actually square the top and the bottom. So 7 squared here is 49. 2 squared is 4. So that's what I'm going to add to my blank. This is then what goes in my parentheses for my factor form, x minus 7/2 squared. So once again, this is the factored form, which is really useful when you are solving. And this is what I actually needed to add into the blank. This is the area of that little square that actually completes the much larger square.